In the previous lecture, I had laid down a way to directly calculate the character, the simple character, corresponding to a particular irreducible representation of Sn, and the approach was the following. We started with the symmetric function pertaining to a particular class, Sl, where L, the class label, could be 1 to the alpha, 2 to the beta, 2 to the gamma, etc. Meaning, a class comprising of elements with alpha 1 cycles, beta 2 cycles, gamma 3 cycles, and so on. For that, SL would be S1 to the power alpha, S2 to the beta, S2 to the gamma, and so on, where Si is the sum of the ith powers of the variables involved. You then went on to multiply this by the totally alternating function in m variables, dx1 ... xm, and this totally alternating function could be expanded in terms of these totally alternating functions on the right hand side, where each term had to have strictly decreasing powers of x, and all possible antisymmetrized combinations imposed by permutations would be allowed. The coefficients would give us the corresponding simple characters. And this dx1 ... xm was the standard result, a product of xi minus xj for I less than j. In other words, x1 minus x2, x1 minus x3, ... x1 minus xm, all the way up to xm minus 1 minus xm, which we could write in a similar alternating function form as sum over p delta p times the permutation operator acting on x1 to the m minus 1, x2 to the m minus 2, all the way up to xm to the power 0. Now this led us to a graphical approach towards calculation of the characters. In the last lecture, we had only looked at the character for one particular class, the class which contains the identity and the identity alone, that is the class with n1 cycles. Therefore, the corresponding function that we would need to calculate is S1 to the L times this capital D. The importance of this calculation is that the simple character corresponding to this particular class always gives us the dimensionality of the corresponding irreducible representation. So, the dimensionality of an irrep of Sn labeled by a particular partition of n could be found out using this. And the approach was as follows. We started with a diagram, the so-called Young diagram, for a given partition. If the partition happened to be 2, 1, 1, as in this example, we would put 2 boxes in the first row, 1 box in the second row, and 1 box in the third row. Of course, if the partition had been lambda 1, lambda 2, lambda 3, ... lambda n, where lambda i's add up to n, and they are strictly non-increasing, then we would end up putting lambda 1 boxes in the first row, lambda 2 in the second row, lambda 3 in the third row, and so on, all the way down to lambda n in the last row, the nth. Note that because of the way in which we write our partitions, with the lambda i's being strictly non-increasing, you can never have more boxes in a particular row than in the row above it. And all Young diagrams have to be built up according to this specification. After we write down the Young diagram, we fill it up according to a standard order. This is what is called, technically, a regular application. The rule is, we are going to fill up 1 box per every S1. Here we are of course going to fill up all the n boxes, ultimately. Now this filling procedure is subject to a very important restriction. At any given stage, the filled up boxes in a particular Young tableau should also give you a standard Young tableau. That means that at any given stage of the procedure, you should not have more boxes filled in a lower row than in any one of the upper rows. In addition, the rule which has to be obeyed during the filling is the following. The numbers which designate the order in which the boxes are filled up can only increase from left to right within a particular row and can only increase down a particular column. If you fill up a Young diagram adhering to this set of rules, you get what is called a standard Young tableau or standard tableau for short. And the dimensionality that we are seeking is nothing but the number of distinct standard tableaux that can be created while adhering to these rules. In other words, in how many different ways can we put in numbers 1, 2, 3 up to n in these n boxes so that the numbers always increase from left to right along a row and always increase from top to bottom along a column. We are seeing this calculated explicitly for this particular partition and hence its corresponding Young diagram in the last lecture. Let me quickly remind you of the results there. The first application of S1 corresponds to filling up one box with the number 1. And the only way you could do that while adhering to the rule that the filled boxes must be a standard tableau is that the 1 has to go in the top corner. Now, as far as S1 square is concerned, you have to fill up 2 of the boxes. 1 has already gone into the top corner. Adhering to the basic rules, there are only 2 possibilities. 1 here would have to be followed by 2 here, increasing along a row, or increasing down a column. That is 1 here will be followed by 2 down here. You cannot have 2 down here, for instance, because that would have left a tableau in which the third row has more entries than the second row, which would have been empty in that case. So these are the only 2 possibilities up to S1 square. S1 cube would mean I have to put in the third entry, that is fill up a third block. If you already had this, the third block would have to go here. But if you had this, 1 and 2 down here, then the 3 had another possibility. You could put the 3 here, which would actually obey the rule, increasing along a row as well as increasing down a column. Or you could have 3 down here, all the numbers increasing down the first column. So S1 cube gives you 3 choices. One choice only starting from this one, which is this. And if you started from this, you get 2 possible choices. Now S1 to the 4 means I have to fill up the 4th block. But now of course you have no further choices. The number 4 has to go in the empty block here. And so you are left with these 3 possibilities. And this tells us that the dimensionality of the irrep corresponding to this particular partition 2, 1, 1 of S4 happens to be 3 because there are 3 different standard Young tableaus corresponding to this particular Young diagram. Now this particular approach is so important that we need to get some practice into using this. So let us take a look at a calculation of dimensions of irreps of S5. Of course, the irreps of S5 are labeled by the partitions of the number 5, and so we start going through the partitions one by one. The first partition of 5 is simply 5 alone, and that means that the corresponding Young diagram would have 5 boxes in one row, and the only possible way to fill this up, rather obviously, is write down 1, 2, 3, 4, 5 in the boxes, right in that order, and therefore the dimensionality of this particular representation has to be 1. There's only one way to do this. Let's come to the next partition, which is 4, 1. The corresponding Young diagram, of course, will be 4 along the first row and 1 in the second row. Now, if you fill up these 5 blocks in a given Young diagram, adhering to the rules, it's obvious that 1 has to go and sit in the top corner. But then, one possibility is you can fill up the first row with 1, 2, 3, 4 and put 5 in the single box in the second row. But you could also do something else. Another possibility could be, of course, put 1 in this corner. There's no choice there. Then keep on filling up the first row, 1, 2, 3, but then put 4 in the one box in the second row and fill up the final corner box here with 5. Or you could do it like this, 1, 2, and then put 3 in this box, fill up the rest of the top row by 4 and 5. Similarly, 1, the very next element could go just below that. That is a genuine, proper standard tableau. And then fill up the rest of the top row with the numbers 3, 4 and 5. In other words, 1 has to go in the top corner, but the first box in the second row could have either 5, 4, 3 or 2, giving you 4 possible choices. What about the partition 3, 2? 3 boxes in the first row, 2 boxes in the second. One obvious way to fill it up would be 1, 2, 3, 4, 5. But then you could go 1, which has to go there. Then 2 could go here, but 3 could come down and then go with 4 here, 5 here. But with this particular arrangement 1, 2, 3, we could also have 1, 2, 3, then 4 here, 5 here. And rather than put 2 in the next position, I could put 2 down here. So 1, 2, and then you could have 3, 4, 5, or 1, 2, then 3, 4, 5. 5 possible ways. 3, 1 square. Well, one obvious choice. 3 blocks in the first row filled with 1, 2, 3, then you have 4 and 5. But then you could put only 1 and 2 in the first row, 3 down here, 4 down here, 5 up here. Again 1 and 2 in the first row, 3 down here, but 4 here and 5 here. That would also adhere to the rules. You could put 1 and 2 down here. Then you could have 3 down here, 4 and 5. Again with 1 and 2 down here, you could put 3, 4 and 5. And 1 and 2 down here, you could put 3 there, but 4 here and 5. Giving you 6 possible choices. The next possibility is 2 square, 1, which again turns out to have 5 distinct ways of filling it up. That has been drawn on your screen right now. 2, 1 cube, which has 2 boxes in the first row and 1 box each in the second, third and fourth row, has 4 ways of being filled up. And finally, the partition 1 plus 5, 1 plus 1 plus 1 plus 1 plus 1 has 5 boxes, 1 in each row, and they can only be filled up in one order, 1, 2, 3, 4 and 5. Now, if you were to take a look at the dimensionalities and these partitions again, you would definitely spot a pattern. You get 1, 4, 5, 6, 5, 4, 1. In other words, the dimensionalities, apart from the 1 in the middle, the 6 in the middle, are coming in pairs. There are 2 one-dimensional irreps, one corresponding to this partition, the 5, the other corresponding to 1 to the 5. What's even more interesting is that if you look at the diagrams, this is the diagram corresponding to the partition 5, all 5 in one row. Here you have the diagram corresponding to 1 to the 5, all 5 in one column. Note here, the 2, 1 cube has 2 in the first row, 1, 1, 1 in second, third, fourth, corresponding to dimension of 4. The other 4-dimensional irrep corresponds to this case, 4 down first row and 2 columns. Notice that this and this are very similar. All you have to do is interchange the rows and columns, and you go from this, which has 2 columns and 4 rows, to this, which has 4 columns and 2 rows. In fact, the same goes for the partition 3, 2, dimensionality of 5, and the partition 2 square, 1, which is again dimensionality of 5. Notice that all you have done is basically flip the rows into columns, and that gives us exactly the same structure in both cases, and that's why you have the same number of dimensions. D equal to 6 for 3, 1 square is a bit of a exception here, for the simple reason that for this particular case, if you were to interchange rows and columns, you get the same diagram back. So this doesn't come in a pair. All other dimensionalities come in pairs like this. So these representations, which have young diagrams which you can get by transposing rows and columns, are called conjugate irreps, or the corresponding diagrams are called conjugate young diagrams, and they always correspond to equal dimensionality. The rigorous proof of that will be given later, but you should be able to sort of intuitively understand why this is the case. Now, while this procedure is simple enough, it can get pretty tedious. For example, if you look at this particular partition, 4th, 2, 1 of 7, the corresponding irrep will be related to the Young diagram with 4 boxes in the first row, 2 in the second, 1 in the third. And what we have shown here is one way of filling this up, the most obvious way of filling this up while maintaining all the basic rules. However, if we were to enumerate all the possible ways of filling this up, this will tend to be quite a lengthy task. There are exactly 35 distinct ways of filling up the Young diagram in this case with numbers 1, 2, 3 up to 7 while adhering to the rules that we have laid down above. So, it would be nice if we had a nice formula which could tell us the number of ways in which this can be done without actually having to go through the hassle of enumerating each and every possibility. It so happens that there actually is such a formula. And this formula depends on what is called hook lengths. So let me try to explain what that means. To describe the concept of a hook length, let me take a concrete example. The example of a Young diagram corresponding to the partition 3, 2 of 5. So 3 boxes or cells in the top row and 2 boxes in the bottom row. Now, the hook length is a number which you associate with each and every one of these boxes or cells. And for example, if you take a look at this particular box here, to figure out the hook length, what we need to do is draw a hook. A hook is a line which enters vertically from below the Young diagram, reaches that particular cell, takes a right turn and exits from the right hand side or right hand edge of the particular row. The hook length for this particular cell is nothing but the number of cells that are being crossed when you go along this hook. In this case, 1, 2, 3. So this particular cell has a hook length of 3. This one, on the other hand, will have a hook which goes straight up and right, crossing only one cell. So this will be a cell with a hook length of 1. The same will happen for this particular cell. You go up, right, hook length 1. For this one, you go up, enter this, turn right. So the number of cells you enter rather than cross, because you are not really crossing this cell, is actually 2. And that's the hook length. Similarly, for this, you go all the way up, 2 cells, 2 more cells to go out, 4 for the hook length here. Let us try to get some practice in calculating the hook lengths for a more complicated Young diagram next. The Young diagram happens to be one which I have drawn corresponding to n equals 14 and this particular partition 4, 3, 3, 2, 1, 1. Now, if we want to figure out the hook lengths for each box, say this one, you go in and out, entering only one cell. So this has a hook length of 1. For this one also, hook length of 1. For this one, hook length of 2, because you have to go through 2 cells in order to complete the hook. Then this one, hook length of 1. And we go here. This is the hook length of 3. Then this cell, you go all the way up and right, going through 4 cells. So this is a hook length of 4. The one on top here actually is a hook length of 1, 2, 3, 4, 5, 6. So this is the hook. The hook length is 6. It's easy to see that the hook length for this particular cell is 1, 2, 3, 4. For this cell is 1 obviously. For this cell is 2, you go up 2 cells then go out. For this one actually it's not 3 but 4 because you go up 3 cells then go out after crossing 1 more. For this it's actually 1, 2, 3, 4, 5, 6 here. For this one is 1, 2, 3, 4, 5, 6, 7. And finally for the top is 1, 2, 3, 4, 5, 6, 7, 8, 9. So these are the hook lengths associated with each cell. So now we have all the hook lengths for all the cells in a given partition. But what good is it? The answer lies in the famous formula for dimensionality involving hook lengths. This is a formula which is very, very simple, but it took around 50 years to be discovered after Frobenius had originally laid down the basic idea behind Young diagrams. And this particular formula happens to be the following. Dimensionality of an irrep of Sn corresponding to a Young diagram, which corresponds to a particular partition lambda, is nothing but n factorial divided by the product of all the hook lengths. So this product has to be over all the cells in the Young diagram. So here, in our example, it's going to be 14 factorial, that's for the n factorial, divided by 9 into 6 into 4 into 1 into 7 into 4 into 2 into 6 into 3. I'm not bothering to write down the ones, into 4 into 2. Calculation itself is pretty straightforward. You write down 14 factorial out in full and then cancel terms between the numerator and the denominator. 6 is cancelled. The 4 and 2 cancels here with 8. Then you have 7 cancelling. 9 gets cancelled. 6 and 4. Well, 6 cancels here to give 2. And then you can get a 7. So the result is 7 into 13 into 11 into 10 into 5. Is a whopping 50,050. It's obvious that enumerating all these possible ways of filling up the Young diagram according to the standard rules to arrive at this result would have been very, very hard work indeed. The hook length formula gives us a quick way of finding out the final answer here. We have actually evaluated the dimensionalities of all the irreps of S5 using the hook length formula here. It's pretty straightforward. I'm not going to bother to go through the entire calculation except maybe just show you one example. For the partition 2 square comma 1, 2, 2, 1 is a way in which you lay down the boxes. This particular cell, of course, has a hook length of 1. This one has a hook length of 1 again. This one has a hook length of 3 because you're crossing 3 cells or at least entering 3 cells as you go to the hook. Here it's 4 cells. Here it's 2 cells. So the formula for the dimension gives us 5 factorial divided by 2 times 4 times 3 times 1 times 1 and simply 5. This of course reproduces the result that we had calculated earlier. And a good way to check that you have understood the hook length formula properly is to at least replicate all the dimensionalities of S5 that we had done earlier using this method. Now, as I've already said, it took nearly 5 decades before the hook length formula could be written down for this simple calculation, the calculation of the dimensionality of a irreducible representation. And the reason behind this is the fact that the hook length formula, while it's very easy to state, is not really very easy to derive. I will give you a derivation which will actually follow from the Frobenius formula that we had started out with in this lecture. And then we will derive a formula for the dimensionality of an irreducible representation, which we will show is actually the same as the hook length formula. That is a rather indirect derivation, but that will have to wait till later lecture. For the time being, we have to take a look at something which is more pressing, which is how to adapt our given graphical method so that you can also calculate characters for other classes using this approach. We will see a very similar approach will work, but it will have to be done with a bit of care. To understand this, what we need to do is go back to our original Frobenius formula and start with D, which is a totally alternating function, and try to understand how things evolve as you multiply by each SI in succession, especially when I happens to be more than 1. To get at the detailed rules, let us go back and take a look at the basic method that we were using. Remember, chi lambda L, the simple character that we are seeking, is a coefficient of the single term x1 to the lambda 1 plus m minus 1 times x2 to the power lambda 2 plus m minus 2 all the way down to xm to the power lambda m in the expansion of dx1 dot 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 xm times s of L. And s of L in particular could be of the form s1 cube, s1 to the alpha, s2 to the beta, and so on, which is s1 times s1 times s1 alpha times, then s2 times s2 times s2 beta times, s3 times s3 gamma times, and so on down the line. So what we do is start with this totally antisymmetric function dx1 dot 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 xm and keep on multiplying by SL1, SL2, SL3 as the case may be. Now this is very important. At each stage, a term will vanish and of course will not contribute to anything in subsequent stages if any two of the powers coincide. So, in order to see how this goes, let's start from the very beginning. In the beginning, we had dx1 dot 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 xm, and the term that we were looking at essentially has an entry x1 to the m minus 1, x2 to the m minus 2, all the way down to xm to the 0. Of course, this is not the only term of this kind. All its antisymmetrized combinations will also be there in the D, but we are going to focus on this particular term. Since we are looking at S2 here, because L1 is 2, we are multiplying this by sum of xi squares. Now, if we remember the rules, there can only be two possible terms here. One term can be obtained by multiplication through x1 square in this sum, which will move this m minus 1 all the way up to m plus 1, increases by 2. And then you have x2 to the m minus 2, x3 to the m minus 3, and so on. There is also one more term that will come about, which is by multiplication by x2 square, whereas this m minus 2 will increase to m. Once again, all the powers on the x1, x2, etc. are unequal, so there is no reason for this to vanish. So this will be a legitimate term. The only problem is this is not coming in the right order, that is in the descending order of powers of x1, x2 and so on. But remember, this is not the only term that's there. All its antisymmetrized combinations are also there. So, just as you have this one term, you will also have a term in which the powers of x1, x2, etc. are in the right descending order. That is the term x1 raised to the power m, x2 raised to the power m minus 1, and the rest the same as before. This can be obtained from this term by permuting the two powers m minus 1 and m, switching them, and because this involves one switch, you will get a minus sign. And note that as a result of this, finally, compared to what you started out with, x1 and x2 have risen in power by plus 1 each. So here you had the first thing increasing in power by 2 without any change of sign. Here you have both the first and the second increase in power by 1 each, along with an accompanying change in sign. x3 square, x4 square, etc. will not give you any new terms, because for example, if you were to multiply this by x3 square, x3, which had a power of m minus 3 before, will now end up with a power of m minus 1, which means the power of x3 and x1 will match, and therefore on antisymmetrization that particular term will vanish. To represent this procedure graphically, what we need to do is have a diagram with m different rows and put two dots corresponding to multiplication by these two powers. In the first case, we could multiply by x1 square to get this, and that of course will contribute to two dots on the first row. The second case is slightly more complicated. Although you are multiplying by x2 square, after rearrangement to put this entirely in a descending order of powers, we actually end up with a situation where we are multiplied by x1 and by x2 at the expense of a minus sign. So to represent that, we could put two dots in the two top rows, one for x1, one for x2. And notice that in this case where all the dots go into one row, you have a plus sign, and here when the dots are distributed over two rows, you get a minus sign. We have also seen that instead of using dots like this, we could also use Young diagrams where we would have boxes corresponding to the entries in each partition for each row, and now you will fill up with two ones corresponding to this multiplication by S2. And here the two ones could go on the top row, or these two ones could go along the first column. In the second case, you will get a minus sign. In order to see a general rule emerge here, what we will do next is look at the case where L1, the very first class index that you are multiplying by, happens to be 3. That is, you are going to multiply by S3 starting from your original determinant D. Now, in this case, you could multiply by x1 cube, that would give you x1 to the m plus 2. All the other powers will be different, so there's no problem there. You could also multiply by x2 cube, which will make the power of x2 overshoot the power of x1, end up becoming x2 to the power m plus 1. And here, this is again in the wrong order. This is not in the descending order of powers, but you can rewrite this by remembering that there is another term originally which has x2 here and x1 here, and by swapping we are going to end up with this case where we swap the powers instead of the indices with the same effect, and now you end up with a situation where you have effectively multiplied by x1 twice and x2 once at the expense of a minus sign. Could also actually multiply by x3 cube in this case. Note that x3 had a power of m minus 3 to begin with. Multiplying by x3 cube pushes its power all the way up to m, which means it has now crossed both x1 and x2 and has become the highest power in this case. But once again, we need to reorder the powers in order that they come in descending order. For that, what we need to do is push m to the front and move m minus 1 back here and m minus 2 back here to end up with this. And this note is an even permutation. You are actually moving m across two powers, two switches, two minus 1s, and hence an overall plus 1. And now you are multiplying essentially by x1 once. Remember, x1 had m minus 1 power to begin with. Now it's x1 to the m. x2 similarly had a power of m minus 2 to begin with. Now it's m minus 1. And x3 ends up with a power of m minus 2, which is also 1 extra. Let us now translate this into a graphical representation by means of Young diagrams. First, let us try putting dots for multiplications. In the first case, of course, you are multiplying by x1 cube, and the power of x1 has gone up by 3. This will be signified by 3 dots in the very first line. In the second case, we are actually multiplying in the final result by x1 square times x2. That's why the power of x1 has gone up by 2, power of x2 has gone up by 1, and this of course can be signified by 2 dots on the first line and 1 dot in the second line with a minus sign. In the final case, we have 3 dots in each of 3 lines, signifying the fact that the power of x1, x2 and x3 have all gone up by 1. And this overall term comes with a plus sign. Now, in order to understand this a bit better, and especially in order to establish a general rule which will work even when we move on to the later stages of the calculation. Remember, here we are only talking about the very first multiplication. We have started with D and multiplied by S3. But later on, we may need to carry out this same calculation. In fact, we will need to carry out the same calculation when we already have done a few multiplications by SIs, and then we need to multiply by a particular SL. Now, the way in which the rule works in general is the following. In the first case, of course, there's not much to say. You just put in 3 dots in the first rows. In the second case, you start with the second row and put as many dots as needed to go beyond the previous row's number at this point by 1. Of course, here we have a completely empty Young diagram. So when we add a dot here, we have already gone beyond the occupancy of the first row by 1. So that's all the dots I can put in here. Then I put in a dot in the upper line and put in as many dots as I need to exceed the number of dots in the previous line by 1. But here, of course, there is no limit. This is the topmost row, so you can put in as many as you want. In this case, of course, we have a total of 3 dots to put, and that's done. In the next case, what we do is we start from the third row. We put a dot. Remember, that's 1 more than what is there here, so that's perfectly according to our rules. But then what we are going to do is put in as many dots here to exceed the number in the previous row. Previous meaning upper row by 1. Done. Again, since the upper row is empty, you can only put at most 1 here. And we go on and put in as many dots that are left. That is, of course, 3. So, these are the 3 possible things that we can do. Just to illustrate what would go wrong, for example, if we started not here, but from the 4th row and tried to do the same thing, this is what would happen. I start here, I can put only 1 dot here, 1 more than the upper row, which is of course empty. Then I can put 1 dot here, at most, 1 more than the upper row, and again 1 more than the upper row, but I have exhausted all possible dots that we can have. We have only 3 dots to put. But now notice that what we have ended up with is a diagram which is not a genuine Young diagram. There is not a standard form because you have more dots in lower rows at the end than you have in the upper row. In our procedure, we put 1 dot more than was there in the previous row, but that was in an intermediate stage of the calculation. After we complete putting in all the 3 dots, I must have a genuine Young tableau in the standard form, which means you cannot have a structure like this. By the way, the reason why you cannot have a structure like this should be clear. From the original algebraic calculation that we did, if we had multiplied by x4 cube, this would have given rise to x1 to the m minus 1, x2 to the m minus 2, x3 to the power m minus 3 as they were before. But x4 happened to have m minus 4 as a power, and multiplication by x4 cube would have made this x4 to the m minus 1, which would make these 2 powers identical, and that would make the whole thing vanish. So this is why you cannot really multiply this expression by x4 cube in the first go. And if you try to do that, you would end up with an illegitimate final tableau. Let us now go back to the legitimate applications of the dots, the so-called regular applications, the 3 that we had done to begin with, and talk about the sign involved. Note that in this case you have no extra sign, you have a plus overall, and that's simply because you are multiplying simply by x1 cube here. This ends up giving x1 the highest possible power, so no rearrangement is necessary. In this, you had actually started multiplying by x2 cube, but then you had to rearrange. And that rearrangement is being shown here in the graph by the fact that two of the rows are getting new dots attached. You had no dots to begin with. Now the second row has one dot and the first row has two. So since this involves two rows, ultimately what we have done is we have started by multiplying with x2 cube, but pushed and switched x2 and x1 with each other. One switch, so a minus sign. Here on the other hand, we have started with x3 cube and pushing it all the way up essentially ended up giving one dot to each of the rows, a plus sign. But this should give you a hint about the general rule. The general rule is if at any given stage the regular application of the dots end up involving an even number of rows, then basically what you have done is you have jumped across an odd number of places and therefore you get a minus sign. With an even application where you have odd number of rows affected, it's going to end up giving a plus sign. And this is the general rule. And to just wrap this up, let me point out that usually we will not put dots in a Young diagram because we need to keep track of the order in which various dots are being applied, and we can do that by using colored dots the way we did before, but we will usually just do this by putting numbers. Since this is the first application, I'm going to put 1. 3 ones on the top row for the first case. 1, 1. Let me remind you once again, this is 1 which is one more than the number that you put in, that were there in the previous row, and then you have to put the rest on the top row. Here you put a 1, one more than what was there in the previous row, one more than what was there in the previous row again, one here, and finally the one left here. And this basically is the idea behind the geometric approach in character calculation. Although this is a very simple situation where we are looking at the very first SL that we are multiplying by, starting from just the determinant itself. In other words, you are starting from an empty Young diagram and putting in your numbers. In this case, just the number 1. Just to make sure that we have understood this clearly, let me quickly give you one more example, the example of multiplying first by S4. In this case, let me just quickly go through the legitimate multiplications that we can do. We can multiply this initial term from the determinant by x1 to the 4, leading to x1 to the m plus 3, the power of x1 going up by 4, and that of course means you are putting all your 4 products or 4 dots, in this case just the 4 ones, in the top row. You could also multiply by x2 to the power 4, that would move x2's power up to m plus 2. That of course would be a wrong order, so we need to switch these two to right. x1 to the m plus 2, x2 to the m plus 1. x1's power has gone up by 3, x2's power has gone up by 1. This of course is not m plus 1, this is m minus 1, which is just the power which x1 had before. You are switching these two. Now, at a graphical level, what we could do is we could start from the second row, putting in a single 1. Remember, one more than what was there before. And that's it. You can't put in more than that. And now you have 3 of the multiplications left, so you put them in the top row. And because you have 2 rows affected, this comes with a minus sign. Let us try doing the next term graphically to begin with. We will start on the third row. Again, maintaining the rule, 1 more than what was there before. 1 goes here and a single 1. Again the same rule, 2 left. And because 3 rows are being affected, this is what is called an even application. You get a plus sign. What about this? Well, start in the 4th row, 1 more. Go up, 1 more than in the 2nd row. 1 more than in the 1st row, and you are left with 1 Only one left to place here, and this is an odd application because it involves an even number of lines, and you get a minus sign. You can of course verify that is exactly what will happen if you multiply by x4 to the power 4, which changes x4 to the m minus 4 to x4 to the power m, and then you have to move it all the way forward, jumping across 3 rows and therefore getting a minus sign. And just to see what would go wrong if you had started somewhere else, suppose that's multiplied by x5 to the power 4 here, I would have ended up with 1, 1, 1 and 1, but now I would have ran out of all the multiplications I could do. I have only 4 ones to play with in this case because L1 is 4, and now I have ended up with a Young diagram which is not a legitimate tableau because you have more entries in a lower row than in the upper one. So this one is of course not allowed. What we have discussed so far involves the first multiplication by an SL acting on the original D. But of course, to calculate the character in full, we will have to multiply by several SLs. That involves a bit of subtlety, and in turn, that will also explain to you exactly why we had come up with this rule that we can put in as many dots in a lower row as one more than that were there in the previous row. But just to check that out, we will have to start small. In the sense, we will start with a single example rather than the most general case. And once we have enough confidence from that single example, we are going to then go on and talk about the most general case. So let us talk about a situation like this. Let's say we are dealing with a case where m equals 5, and at some stage of our calculation, we have arrived at this term, at this diagram with 4 dots in the top row, 2 in the second, 1 in the third, and that essentially means we have multiplied our original term from the determinant x1 to the 4, x2 cube, x3 square, x4 to the power 1, x5 to the 0 by x1 to the 4, x2 square, x3, and this has brought in a plus or a minus sign depending on the way in which this was actually done. Remember, I am not saying that all these dots, the 7 dots that you can see in your figure, were applied in one go. This could have been a result of, say, S1 times S1 times S5, or S1 times S1 times S1 times S4, or some other way of arriving at this. So, depending on how you arrived at this, you could have an overall plus or minus sign. The question now is, suppose after this we want to multiply, let's say by S4, that is x1 to the 4 plus x to the 4 plus x to the 4 and so on. Once again, let me remind you that when I write this is just a typical term in the original determinant. All its completely antisymmetric counterparts are also there. Now, one thing we can do is multiply by x1 to the 4. That of course is going to raise this power here to 8, which means the overall power of x1 to 12. That is definitely the highest power here, and therefore the order that we had, the descending order of the powers of x's, that is being maintained. So no further manipulation is necessary. And diagrammatically, all you are doing is the 4 dots that you need to apply here, the blue dots in this case, I will just apply to the front row. And since only one row is affected, you have to put in a plus sign. Of course, the rule about being able to put at most one above the previous row does not apply for the very first row. The very first row has no previous row, and therefore there is no limit to the number of dots you can put there. Unless, of course, you are going outside the bounds of your Young diagram. That has to be kept in mind. Here we are assuming that the partitions that we are using are large enough so that none of these dots are outside the boundaries of the Young diagram. Now the next step, multiplication by x to the 4. Now let's break this up in steps. If I multiply by x to the 4, you have started with x2 square here. A multiplication by x to the 4 raises this to x. x2 to the power 6. But now let's look at the overall powers of the x's. x1 is at 8, the power that you had before. x2 now is at 9, 3 plus 6. x3 is at 3, x4 is at 1. So the powers are 8, 9, 3 and 1. Not in the correct descending order of powers that we want. So what we need to do is use the fact that there are alternating terms available in your original determinant. Or you can also use the fact that this product is also an alternating function equivalently and switch these two powers in order to bring this to a descending order, 9, 8, 3, 1. The switch of 2 will take minus sign. And now, note that if you take out your original term from the determinant, x1 to the 4, x2 cube, x3 squared, x4, what you are left with is 5 powers of x1 to the 9 here, x1 to the 5 here, and 5 powers of x2 and a single x3. So here what we did was we started to apply the dots in the second row, and okay, let me just do it live so that you can see what's happening. You apply dots, as many of them as you need to go one beyond the previous row, and then you stop applying dots to this row, apply the rest of the dots to the previous row. We will reveal the mystery of this one beyond the previous row soon, but for the timing, just take that as a rule. Now this is an odd application because it involves an even number of lines, so a minus sign. That's a graphical statement that we are making. Of course, the minus sign here comes from the fact that x1 and x2 were involved, and we have ended with more powers in x2 at the end, so it has switched the powers. One switch, one minus sign. Let's come to x3 to the power 4. x3 to the power 4 would end up giving the power of x3 a value of 5. And so if we collect all the powers together, we now have 8, 5, 7 and 1 for the powers of x1, x2, x3 and x4 respectively. Once again, we have violated the rule. We should have them in descending order. So we have to go 8, 7, 5, 1 with a minus sign because we have switched these two. Now, of course, once again take x1 to the 4, x2 cube, x3 square, x4 out, the original term from the determinant, and you are left with 4 powers of x1, 4 powers of x2, 3 powers of x3. So how does this work? Again, let me show you how this works live on the graph. You start with the third row, apply as many dots as necessary to go beyond those already in the second row by 1, and then stop adding dots to the third row, and now add dots to the upper row, which is 1, and before you can exceed the number in the top row, you have run out of dots. So this is your scenario. This is a perfectly legitimate Young diagram at the end, and therefore this is exactly going to give you a legitimate term. And because 2 rows have been affected, you have added dots to 2 rows. This is an odd application, you get a minus sign. The next possible term could come from a multiplication by x4 raised to the power 4. Now notice that you did not have any x4 to begin with. You had only x1 to the 4, x2 square, x3 at the previous stage. Now you have put in 4 powers of x4. But that ends up making the powers of x2 and x4 equal, and anti-symmetrization ensures that this thing will cancel out and you get 0. Now let's see what this tells us at a diagrammatical level, and once again let's do this live on screen. So if you want to start adding dots in the 4th row, I will keep on adding dots until I exceed the number in the 3rd row by 1, so that's it. Now I have to keep on adding dots until I either run out of dots or I exceed the number in the 2nd row by 1. That is, I add 1 dot here, I still have 1 more dot to go, so I add this, I have gone beyond the 2nd row. Unfortunately, I have run out of dots at this stage. I have no more dots to put. So this is what my diagram would have looked like. But this is not a legitimate Young tableau. There are more dots in the third row than in the second one. Remember, the number of dots can never increase as you go down the tableau. And therefore, this is not an allowed diagram, which actually is reflected by the fact that multiplication by x4 to the 4 would have given you a term which vanishes identically. That doesn't mean, however, that we have come to the end of the line. We still can multiply by x5 to the power 4. And if we do that, we now have this which we already had before at the previous stage, and a further x5 to the 4. Notice now that we have x1, x2, x3, x4, x5 with powers of 8, 5, 3, 1 and 4. Wrong order. So I have to make it right. I have to make the 4 move ahead of this and this to put it here. But because we have to jump across 2 places, this actually gives you just a plus sign. And now taking out the original term from the determinant, the extra things, which are the extra dots that we are putting, are just x1 to the 4, x2 square, x3 square, x4 square, x5. So let's do this again on screen directly. I am putting a dot in the 5th row. I have left a space here. I can put only one dot there. Remember, one more than the previous row. Now I can put dots in the 4th row, but I have to put one more than the previous row. That is 2 dots here. We are left with one more. The 4th dot which goes here. And now we are done. Note that this is a perfectly legitimate Young tableau, standard tableau. And so this will contribute with a plus sign because 3 rows are being affected. This is an even application, an application which is over an odd number of rows. Once again, let me remind you, the fact that 3 rows are affected are basically reflected here by this fact that 3 of these terms are out of order. You have to jump across 2 of them to get to here, leading to a plus sign. With this example under our belt, let us now take a look at a more general situation. So we are considering a case where we had m pieces to our partition, and at any later stage of the calculation, after we have multiplied by SL1, SL2, etc., we have arrived at a typical and permissible result. That is, the original term x1 to the m minus 1 xm to the 0 has been multiplied by nu 1 powers of x1, nu 2 powers of x2 all the way down to nu m powers of xm. And we are going to focus on a particular x cube for the time being. Now, because we need the overall powers of x1, x2, x3 to be in a strictly descending order here, remember all powers have to be different, and we are going to typically take a term which has the powers in descending order. All the other terms will be considered anyway because of the antisymmetry involved. So we must have nu 1, nu 2, nu 3, etc. being strictly non-increasing. That is, nu 1 has to be bigger than or equal to nu 2, nu 2 has to be bigger than or equal to nu 3, all the way down to nu m. Now this is the condition for this particular term that we have arrived at to be a legitimate term. That is, this is what will give you a legitimate standard Young tableau with number of dots in a lower row not exceeding the number in a higher one. Now, if the next multiplication in the series is by SR, that is, by the sum of the rth powers of the xi's, will a multiplication, a typical term of x cubed to the r, contribute to the final result? Now, in order that x cubed to the r multiplication at all contributes, we must ensure that this power that we end up with, we originally had x cubed to the power m minus q somewhere here, and we have a new q from the additional multiplications we have already done, So this is what we already had as a power. We are now multiplying by x cubed the r. Now for this to contribute, there must be no such power of nu q plus m minus q plus r among the other terms. In this case, of course, because we have strictly decreasing order for powers, we only have to look for powers of xp for the values of p which are less than q. And there you must have this condition. There must be a p such that our new power, nu q plus m minus q plus r, exceeds nu p plus m minus p, the power which is already there on xp, and does not come all the way up to the power that is there in the next term, that is the previous term. The power of x to the p minus 1, which, remember, is nu p minus 1 plus m minus p minus 1, but that becomes minus p plus 1 after you open up the brackets. So this condition is simply stating that the power that x2 has after this multiplication is different from all the powers that are already there for the previous xi's. Now, if such a p exists, then we have a contribution from this term, and the contribution simply will become the following. We are just going to end up multiplying xq, which had a power of nu q plus m minus q, by a further x to the r, and this is what is going to contribute. But now notice that this power that we have is not smaller than these powers. In fact, it's actually larger than this power and smaller than this one. So this is not in the correct descending order. We can bring this to the correct descending order simply by first shifting this whole term here, which we can always do. After all, these are ordinary numbers, multiplications commute. But now what has happened is the q is in the wrong place. The powers are now in descending order, but the q has come in the wrong place. Q should be back here. So what we now need to do is permute the indices so that the q goes back here. Of course, the same thing could have been done by keeping the q put and switching this all the way up until it comes here. As a result of this permutation, this index becomes p, this index becomes p minus 1, the next index that was p minus 1 becomes p minus 2, all the way until you have this index becoming q. Now this involves pushing this q back through q minus p plus 1 places, actually q minus p minus 1 places. That would give you a minus 1 times q minus p minus 1. But that's the same as minus 1 to the q minus p plus 1. The one term that I've written here as a sign. So this is your final form, where all the indices are actually in the order 1, 2, 3, p minus 1, p plus 1, q plus 1, and so on. And the powers are also in nice descending order. Now that we have done this, let us take out the original powers that you had in the determinant. These were the powers you already had to begin with, and these were the powers you had after the previous stage. As should be pretty easy to see, the only x's for which the powers have changed are the following: xp, xp plus 1 up to x cubed. All the rest have the same powers that they had at the end of the last term. In order to see this a bit more explicitly, let me just write down what was the situation before. This was the original term from the determinant. The terms written in green are the terms for which the powers have not changed at all. The terms in red are those for which the powers have changed. Note that xq had a power of nu q minus 1 plus m minus q plus 1. Now, it already had a power of m minus q from the determinant. If you take that out here somewhere in between, what is left is an extra power of xq to the new q minus 1 plus 1. So number of dots in the qth row, indicating the number of powers that you will have, was nu q to begin with, but now it has to be nu q minus 1 plus 1. So you have to keep on adding as many dots to the qth row as is needed to exceed the number of dots that were there in the q minus 1 row, the previous or higher row, by 1. This basically is the seed of where this mysterious sounding plus 1 rule comes about. To see this in more detail, let us take a look at precisely those terms which have changed. So these are the terms that were written in red before. Notice that what this means is that, as we have said, you have to add enough dots to the qth row till it exceeds the number of dots in the previous row, which is still nu q minus 1 at this stage. Remember, we are adding the dots starting from the qth row. We have not added any to the previous row yet. The term before this would have been xq minus 1 raised to the power nu q minus 2 plus 1. So you have to again repeat the same for that row. That is, keep on adding as many dots until it exceeds by 1 the number of dots in the previous row, which, remember, is still nu q minus 2. We are now going to change the number of dots in the q minus 2th row by looking at x to the q minus 2 to the power nu q minus 3 plus 1, which is here, which I have not written down. And this again means repeat as you go on. This keeps on repeating all the way up to xp plus 1 to the power nu p plus 1. Again, the p plus 1 is 4. You keep on adding dots until you exceed the number which are still there in the pth row by 1. I have not added any dots to the pth row at this stage. And the rest of the dots, rest of the r dots, all go in the pth row to make up this. Note that basically what this is telling you, this condition that we had, is that the number of dots that you have now in the pth row, which is nu q plus p minus q plus r, is actually less than or equal to nu p minus 1, the number of dots in the row above that, which has not changed in the process. And this ensures that the resulting table that you have, the tableau that you end up with, is still a regular tableau. You don't have a row jutting out from below. All of these are still of the right shape. I'm pretty sure all of you have already spotted one situation where this particular inequality is not relevant at all, and that happens when this power nu q plus m minus q plus r turns out to be bigger than nu 1 plus m minus 1. This was the largest power in the expression before you multiplied by xq to the power r, but after the multiplication, this has become the largest possible power. In other words, this term has moved up so that it would now constitute the first row of your diagram. Since there is no higher row in this case, there is no upper bound to this quantity. Apart from that, for all other cases, this inequality is relevant and it will ensure, as I said, that you actually get a regular table. Now, as for the sign for this diagram, the basic idea is pretty simple. All you have done is affect a number of different rows in your diagram, in fact exactly p minus q rows, and if p minus q happens to be even, you are going to get a minus sign. Remember, the factor was minus 1 to the power p minus q minus 1. Now that we have the complete characterization of the graphical method at hand, the next task should be to apply this to calculate characters for certain non-trivial classes. I actually intended to describe a detailed calculation in this lecture, but that will make this particular lecture, which is already long enough, way too long. So we will have to wait for a demonstration of this explicit calculation, as well as proofs of the hook length formula and the original Frobenius formula till the next lecture comes up. Bye till then.